Yes, as you can see today, we're going to talk about factors. But let's see what we had before last class. Okay, so last class, before starting, thank you so much for many of you guys that completed your course survey. Thank you so much. And still 60%. I like to bring it up to about 80%. If you still didn't complete the course survey, please and please do that today. And this is gonna help me a lot to know what I did right, what I did wrong, and I fix it for next time. I think in general we did good coverage, so many amazing topics covered in this class. But for sure we can make it better. And this is up to you guys. I want you lets me know if something was good or something was bad. So let me know. I want you guys that still didn't complete your survey for course survey fall 2025, please complete it. It just takes 5 minutes for you guys, even less, and it's very helpful for me and for all the class. And because I will continue, I will love to continue teaching this course again, and it's going to be helpful. Thank you so much. Okay, so let's get started. So we covered factor graph, and we explained how we can model probabilistic models, probabilistic perception, kind of perception, model it with like probability. And last class, we explained how we can change probability to optimization, because changing probability to optimization is the main part, you know. And in optimization, you can find unknown variables that we call them random variables. Why random? Because they are uncertain. When I'm talking about randomness, it doesn't mean that this is by chance. It means that we have some mean and some variance. We have some actually distribution around that point. So we talk about maximum a posterior. Maximum a posterior is the best estimation ever exist. Maximum a posterior, again I repeat it, is the best estimation ever. Why? Because it's like a mathematically explained probability of something given some observations. So, and when we maximize this probability, if we find this probability in a closed form, in the best way, that solution is an optimal solution. However, sometimes we need to actually do some approximation or do some assumptions. Like, for example, most of the case we assume that the noise is Gaussian, for example, to make everything easy. That makes this optimization not just not optimal, but approximately optimal. But it still is very, very good compared to other methods, and is explainable too, you know. So in general, factor graph is one of the best estimation that you can have if you learn it properly, because it's not easy to understand, kind of. But what we're gonna cover today? Today we're gonna talk about what is the steps, what step we need to do to design a problem using factor graph optimization, using factor graph modeling. Any kind of problem that is kind of predicting, if you have in that problem some actually information, prior information we call it, and some likelihood. And likelihood is like a measurements likelihood around it. Is some measurements there and some prior there. We can write it up as a probabilistic model. And this probabilistic model can break down to factors, and that has some steps that we need to define the factors, we need to formulate the inference as a maximum a posterior, and then solve the maximum a posterior using like normal methods, like for example Gaussian Newton methods or Leeuwenberg Marquardt LM method, that we're gonna see that today. And the next class we're gonna talk a little bit about some libraries in in actually Python for that, especially GTSAM and Georgia Tech. SAM is coming from actually smoothness and mapping. So GTSAM is a open source library for like SLAM problems. Normally, factor graph optimization can be implemented using GTSAM, and it's open source. I already installed that in on my Windows. However, is not easy, but I have the steps in your lecture notes. I think is it for this week or the next week. Anyway, I'm gonna give that to you how you can install it if you want to work on that. However, we're not gonna have any project based off that. But if you want to add some part of what we learn based on factor graph for your final project, that's going to be extra mark. I'm going to give you extra mark based off that, till like 5 mark extra, if you like to work on that. But you need to let me know, and I supervise that if you want to do that. That's going to be the topic of today. So let's see how can go forward. But anyway, factor graph is very good method for robotic perception. I hope you guys understand the value of that. Why is good? Why is amazing? I can count some of them, but you can find more about that. However, it has some problems as well, but in general, is compared to other methods, is much better. So first is very modular method. Is very modular. Why is modular? Because for each sensor, for each like a motion model, for prior information, you just can have one factor. That's it. Just one factor. You just need to define a factor, some noise for that factor, and likelihood of that factor, and it's very modular. And this modularity help you to expand it easily. If you want to add another sensor to your robot easily, you can add just another factor and just go for that. Is it scalable? It means you can it support very large problems, and in different as it's not just for robotics. You can use it for my new project is actually implementing the factor graph model for a smart grid. That's something amazing that I just did proposal now, but I will work on that soon. Or another thing that I want to work on that is a smart lane markings. Can you imagine lane markings be smart? And they make a factor graph, they communicate to each other, and they adjust their it's so advanced. It's so much things you can add to that. A smart lane marking is amazing project. That first I need to make a paper based of that, but because I don't want anybody else come and um, like put their name on it. I need to first write a paper before distributing information about it, and so much more, especially considering or implementing trust between multi-robots. When you have multi-robot collaborating with something, implementing with factor graph is the best idea. In factor graph, you even can have loop. So loop means you are seeing something that you saw before. So when you see something again, you can fix your problems that you had, your noises, your drift that happens. That's something amazing. Is it scalable? Is actually it has a sparsity. Why it has a sparsity helps to can run it in a very fast inference, in a very what we call it, real time. You can run it in a real time way because it's a sparse. A sparse means each factor is just connected to very limited random variables. Is not a lot. So this sparsity helps to use some algorithms that work with the sparsity to can do inference very fast. Is very flexible with fusion. So we always have problem with fusion, especially when you are dealing with multiple sensors, and fusing is a big deal. And fusion is embedded inside factor graph, kind of, and is graph. So you can visualize it. You can see the result. It's not just math and formula and it's however, it's kind of, you need to have lots of background to understand it. That's why I also consider that as a benefit, because not everybody can understand it. But if you understand it, you're gonna be in ahead of those people. So that's why I think, and that's the future of. I'm sure this is the future of actually robotic perception, like doing like perception based of probabilistic perception. And the visualization is amazing and is very in line with maximum a posterior. And I told you maximum a posterior is the best estimation ever. So is the factor graph gonna at the end break down to maximum a posterior, and you can do updates or optimization. You can do incremental optimization to solve it, and it's much more, so much things, and reusability. You can reusable. If you use a graph for that, you can reusable for so many other things, because you made a general way to explain one problem. Is a general way. Okay. However, it has some disadvantages. Like one of the disadvantages is that is you need to initialize the problem. That's initialization. There is, of course, the initialization is always problem. You need to start with something and then make it better. Like for example, in path planning, when you have source and destination, you always do initialization. Like for example, you have source and destination and lots of obstacles around it. You want to see what is the best path from source to destination. That is source and destination, for example. So you need to have an initial path. Because okay, the best path for initial path can be a straight line. We don't care if it's path. Oh, need to go bring this down. I don't know why it's not showing my picture. Okay. Oh, you know what? I'm gonna go with this and bring it here. Yes. Okay, so maybe this green line be an initial path and then do optimization. So I think this is for most of the problem can happen. And then when we do optimization, it can find, for example, the best path that not hit with obstacles. That's a path planning problem that you can, next class, I'm gonna implement this in the class. in I already wrote the code for that. So initialization is one of the problem. The other problems mostly coming from, you know, complexity kind of, that I don't think that's a problem. If you be experts, if you understand the math behind it, you are ahead of others. So if it's a complex in kind of things and it's not easy to understand for beginners, that's good for you guys, because you understand it and you can use that. And required some information, like for example, you need to know some probability stuff, you need to know noise model, for example, you need to this stuff. And also another point that is important in factor graph is that you need lots of memory. You need memory, not just computational, processor, for example, because it's a sparse processing is not that problem. It's a sparse. Most of the values are zero. You're just dealing with multiple numbers. But the point is, you need to, if the factor graph become huge, especially in a SLAM problem, simultaneous localization and mapping. Imagine you are going with a LiDAR in a city and you are collecting all this information and you put them in a graph, factor graph, and when you go inside, there is lots of factors and values and they need to save somewhere. So that's a memory that you need to use. So however, that's, I think, is always problem, but with improvement that happening for new processors and memories, I think that's going to be solved soon. However, all of these things that I mentioned, there is so many ways to deal with them and fix them as well. But in general, factor graph right now is one of the best method that you guys as a robotic engineers need to know if you want to be successful and be ahead of others. I hope you know the value of that and start working at least for your project, next projects, or next classes. Use that. I haven't seen any other professors in your department still working in that, but I always introduce people. Maybe I make some conference, the presentation for other professors if they are interested. That should be good. Okay, let's go ahead and see what is the steps that we need to do. Imagine we have a problem. We have a prediction problem or estimation problem, and we want to implement it as a factor graph. So what we need to do? What we need to do? So the main point is to actually see if we can break the problem. First of all, as a recap, the factor graph is a bipartite graph. We explained that last class, so I'm gonna explain it again because it's next. We want to see what is the factor graph. If you want to design something based on it, first we need to know what is that. So that is a bipartite graph. So it's a bipartite graph means a graph that the nodes are different. Most of the graph that you've seen before, they have just a node and edge. Nodes are something and edge is relationship between nodes. But in here we have different type of nodes. Some nodes are we call them states that unknown values, this x's for example. Most of the time, to be consistent, we consider them as a circle, empty circle. Right? Computer like that, you can write that on it. So we have some states. That states are unknown. In so many robotic applications, like for example, trajectory of the robot is unknown. In some advanced problems like SLAM problems, we also have landmarkings that they are also unknown. we don't know landmarking position too. We might know some information about them, like, for example, shape of them. For example, yeah, that's going to be prior. But in Islam is one of the hardest problem that you're going to see in robotics, because at the same time you don't know your position, but you just want to find your position based off something that you don't know even their position. But at the same time you are fixing everything together to at the end, and you are guessing you're gonna see a loop somewhere to fix everything, because loop is always loop happening in factor graph, but in BaseNet you couldn't have loop. That's why we said, okay, BaseNet is good method for actually probabilistic models, but factor graph is better. So that's why we moved from BaseNet to factor graph. However, we want to understand factor graph, you need to know the basic of factor graph is BaseNet. Anyway, that's factor graph, a bipartite graph including some unknown and some known. Those things we call them factors. Factors are based off measurements. Some measurements you read them from environment. Some measurements is inside the robot, like odometry, IMU, those things you just read them. And some factors are relationship between two states. Like this is, for example, this box here. Oh, sorry, this one. This is showing relationship between x0 and x1. This relationship coming from the actually dynamic of the model, like IMU or odometry, that give you how this is changing, how is delta x, delta y, if it's theta, delta theta. So that's coming from that. We're going to talk about those. So we want to see this is factor graph, a bipartite graph. You have some unknown things, we call them states, and some known measurements that we call them factors. These measurements or constraints, we also can consider constraints. So for example, anybody can tell me what is the constraints in robotic? Any ideas? You can open your microphone if you want to talk. Any constraints we have in robotic? Like for example, this is a robot, this picture that I draw here, and a robot is moving. What kind of constraint we can have here? Any idea? Like is, for example, velocity is a constraint? Like for example, is an autonomous car. Do you want to consider like maximum speed for that? That can be constrained, isn't it? Like for example, you are driving in a highway in a future world highway, maybe people are inside the cars, but cars like collaborating to each other, and we have a rule to they have a certain speed, they need to adjust their speed to each other. We want to be consistent, consistency is a very important point we need to consider. That can be a constraint, isn't it? You need to see, okay, all of my robots, all of my cars around me in a highway driving with 100 kilometers per hour, and I need to adjust my speed with them. If I draw even less, that's problem too. However, you probably has a certain amount. You can drive in a highway, for example, between, I don't know, 80 to 100 or 110, for example, maximum. This is the range. But at the same time, you need to follow the other cars traffic as at the same time. You need to adjust yourself with others. So that's a constraint. Actually, I have a project about that too. I do factor graph, of course, to implement consistency between multiple agents. They need to just adjust themselves based off others. And that can be implemented using factor graph. That's constraint. I wanted to mention that the constraint is that. So this can get implemented using factor graph. That's important. And measurements too. Sometimes you want to get your distance to, the robot. Robot wants to find distance to the wall, to the obstacles. We don't want to be too close to them. We want to have a certain threshold. Consider that the distance between us and robot and other robots or obstacles. So that's also some constraint as well. But measurements, we can measure too. Measure that is the distance. So we have measurements constraint. Anyway, they are going inside the factors. So we just have factors and unknown states. And relationship between these two coming to the factor graph. So steps that we need to do is just a couple of states that we need to consider. First state is to define the probabilistic model. We need to see, is any relationship between unknown and known? We need to find this one. And this is called posterior density. We talk about that a lot. We want to see this, but this posterior density always can break down using Bayes rule. If you remember, we can see this as a Bayes rule. We can say this is P of X and P of Z given X. And this is a proportion. Remember, this is proportion because we eliminated the other part that is not related to X. We don't care about them because it's going to go to maximization and then change to minimization with log and minus log. And change this multiplication to addition because multiplication is not good for optimization. Addition is good. And we're going to go for that. That's the first step. Can we define this or not? So that's the first step. The first step is to define, okay, here is a theta. Theta means everything, not just X. Even land markings also consider part of the unknown too in a SLAM problem, you know. A SLAM problem, the land marking, position of land marking, I mean. Okay, so that's the first step. Can we define the problem as a probabilistic model? Yes. If we do that, next step is to construct the factor graph. Construct the factor graph means specify what is the unknown, what is known, kind of drawing this picture, drawing this factor graph. That's the main part. After that, after this, we need to see how this part gonna break down because this part gonna make factors. This is prior factors. Prior factors. And this is measurements factors. We need to construct factor graph. Constructing factor graph means find states and factors. Then we need to go inside factors. We need to see, okay, if there is a collision factors, if it's obstacle avoidance factors, if it's a smoothness factors, if it's odometry factors, if it's I don't know, consistency factors, if it's wind factors, if it's ocean current factors, they all can be factors, you know. You just need to find, is in these factors anything that we want to optimize? That's important part. Is in this factor anything we want to optimize? Is any error there that we want to make it better because we want to change it to optimization, remember? So we need to find that part. Is anything we want to improve? Yes, for collision, for example, you want to actually kind of find the error between your position and the obstacle position and make this distance as much as you can. You don't want to be close to that. That's one of them. That's good. for wind, for example, you want to find a position that has a minimum effect on wind. If the wind is going this way, you just move your robot kind of to not affect in that. For example, another thing, I just try to open your mind how amazing you can define factors. Like, for example, you are defining a robot that's supposed to go to the desert area. In desert area, you have hills, you have different places. You need to see how you find your optimal trajectory to go to destination to not deal with these um, factors. Like we call them consumption factors, like a battery consumption. That's also another thing. If you go, for example, in top of the hill, that's gonna make lots of energy for your robot. You need to find a way to don't waste your energy, don't waste your battery. That's called energy factor, or energy consumption factor. So anyway, we need to find these elements. This element showing H is predicted measurements, predicted measurement, and this is the real measurement. A real measurements coming from the sensor, predicted coming from the model. From the model you find, because you want to optimize your model, you want to make your model better, you want to make its theta better, but you at the same time you read some information from the sensor. Like, for example, you have lidar give you for example, distance to obstacle, and you at the same time you predicted your distance to obstacle, and you measure these two and you find the error. So error is something that you want to optimize. This is also we deal with that a lot. Remember, in neural network we had same thing. We find this error, we find that we call that cost function or loss function, and we wanted to minimize the loss. Same way, actually I can say this method is very similar to that in terms of optimization part, in that gradient descent method that you were using in actually neural network. We are using same way too. We are using not gradient descent, but Gaussian Newton method is kind of similar to that. They do iteration. They do iteration too. In that time, you also had iteration epoch. Remember, you were repeating and repeating to find the best way. We are doing the same way. We are doing the same thing. That's just the same. We do derivative, and we just move in the against the direction of derivative to find the maximum or minimum. Same way. Okay. So that's the error part that we want to minimize. The next part is to bring everything down to one single MAP problem. So if we have multiple factors, all these factors gonna make one error, and these errors after getting log and minus log, minimization, maximization gonna change to minimization, and those products gonna get summation. So this becomes summation, and the problem completely changed from that nonlinear complex exponential family to a sum of actually a square method. Sum of a square. This is a square method. Sum of a square. However, this is a square. This is Mahal distance. This is not just a normal distance. We want to normalize it. We know Mahal distance is a difference between two distributions. It's not just two values, x and y. is the distribution of x and y. We consider actually uncertainty around them too. This uncertainty coming in this sigma, and that's the beauty of that. So that's it, and the rest is just well-known algorithms like Levenberg, Margard, or Gaussian-Newton. And Gaussian-Newton and Levenberg-Margard are very similar to Gaussian, the two actually the method that we had before. And iteratively we can solve them. Maybe not today, we're gonna go for the optimization part, but next class is just a couple of, maybe in half an hour we can explain that. But today we're gonna see some samples of GTSAM, and GTSAM already implemented. I just need to call the function, and it's gonna do optimization by itself. But I wrote all the code. I have the codes by myself too. I can share with you if you want. But in GTSAM is all implemented, and GTSAM is open source too. But the source is C++. But you can use it with Python as well. Okay, so that's the steps. So we have 4 steps: defining the problem as a probabilistic model, construct the factor graph, defining errors, or residual. That's a residual. I forgot the word that time. That's the residual. And after residual, we can write all the problems as a one sum of actually squares. Sum of squares. Sum of squares. It still is nonlinear. It still is nonlinear because square is not linear. But you can get differentiation. You can get differentiation of that. So because the method is like that, we get differentiation and move to that direction, against of that direction, because differentiation showing the increase, we need to go to the decrease part because it's a minimization, remember? That's it. Let's see how we can do for some sample example. The best sample example is a SLAM problem, but a very simple a SLAM problem. We call it toy SLAM problem. In this SLAM problem, the robot moving from one position to the others. We have some odometry. The odometry coming from, for example, IMU give you the delta x, how much you are moving, which direction you are moving. And also you have landmarking. Landmarking, you also have some sensors give you distance to landmarking, like, for example, LiDAR. And you have these 2 values. And this is the shape that you can see. This is the main part. But you are not certain. You have drift. When you use odometry, we know that we did example a couple of weeks ago, yes. When you are just dealing with odometry, you have drift. You're supposed to be somewhere, you're somewhere else, because you are adding errors together. Eventually it's add, and grow gradually, and we need to fix it. When we have measurements also uncertain, when you read, for example, distance to the wall is not exact one. So this is the time that we need to go for actually probabilistic models. So we need to deal with P of X or P of theta given Z, and you can find the proportion of that based off prior and likelihoods. Prior and likelihoods. Another problem, how we can fix these drifts. These drifts, the only way, there is actually another way too. Another way is to use another outside sensors like GPS to fix it. This is one way. But if you don't use that, or you want to make more precise values, you need to have kind of fixing by making loop. Making loop in Islam called loop closure. Loop closure is another. We have loop closure here, but loop closure in factor graph is easy to implement. You just need to have another factor, easy, another factor, call it loop closure. If in that you see something that you saw before, so if it's previously seen, for example, that landmarking, you can make a loop. And when you make a loop, you can fix all those drifts. That's the advantage of this. So the SLAM problem normally doing two things. Estimating trajectory, that is x, and position of landmarking, these two things. So that's the main part in a SLAM problem. So that's the first part. The second part is can we implement it with a factor graph? Yes. In factor graph, we need to specify positions. We call them x. Landmarking, we call them L. Positions are x and y and also theta or yaw, like showing the angle. And we also have position of landmarking. So, and factor, this is unknown values. We also need to have factors. So in this example, we need actually some prior factors. Prior factors, for example, some information about landmarking, shape of them, whatever. Or what else? If we know the initial points or start points, that's also prior. I didn't consider prior in this, but prior is also another factor we need to consider. But odometry and landmarking is, landmark measurements is factors that we need to consider. Odometry give you U, that U is delta X, delta Y, delta theta, for example. And landmark measurements give you distance to obstacles. So you have these measurements. Based off them, you can have factors. Oh, I already, and draw the factor graph. You can draw the factor, because the factor graph gives you all the idea. If you forgot something, you can find it here. Like as you can see, you can't connect two states together directly. You need to have something between, and that's factors. As you can see, M's are measurements factors of landmarking. This stands to landmarking, and this red one is an initial position, and the black square is relationship between x0 and x1, or xn and xn plus 1. Okay, so we make this bipartite graph, and we actually consider all the factors over there. We consider all the factors that we have in this graph. So this graph is the main part. So in step 2, we also need to draw this graph. Drawing this graph is very general. As you can see, between x1 to xn minus 1 is just repeating. It can repeat. Next step is to go for factors. For factors part is the important part. For different factors, we have different method to compute them. Like this is for measurements that coming from reading. This is the robot, as you can see in this picture. Use for example, laser to detect the distance to this chair. This is the value that we read using the measurements, like LiDAR, for example. We have these values after reading, and we also can have that based off prediction. So we have some prediction measurements coming from the math that we actually have. So predicted measurements is actually this H. In this H, you have robot's position, a state of the robot, and a state of the landmarkings, and you compute this this predicted measurements, these predicted measurements. And then, because the idea in factor is to find the residual, because you want to maximize it or minimize it, minimize the residual. You want to minimize the residual. You want to make difference between predicted measurement and real measurements minimum. So you need to find predicted measurements and then read information from sensors. The definition of actually measurements coming from measurements model. In measurements model, we add some noise, and we are assuming this noise is Gaussian because we want to make it simpler. And most of the noise actually Gaussian as well, because especially if the noise is additive, we can prove it that this is Gaussian. And there is a theorem for that. And for measurements probability, we can find the likelihood of measurements. This is the likelihood. Likelihood of the measurements is an exponential family, and this is showing when our measurements is closer to predicted measurements, you have higher probability. That's it. However, this exponential also going to help you when you get log, exponential going to get disappeared, and the maximum and posterior problem going to change to just a square, sum of a square problem. That can be linear very optimally. And find the cost. This is the cost part. So done. So for each factor, we need to find this cost. This cost is the main part that we need to put it in that maximum and posterior and done. Even if you know this, doesn't need to go for other part. You just need to find the cost of z given all those unknown or likelihood. This is the cost of the likelihood cost actually. This is likelihood, and the cost coming from the likelihood. And cost in exponential family is going in this distance, Mahal distance between prediction measurements and actual measurements. Okay, for prior information, we do the same. In prior information, you know actually some nominal value, like for example, if you know, for example, the position, a starting position is x, so you already have that with some uncertainty for sure, because this mu is also is not certain. It has some noise on it. It has some uncertainty on it. If you consider that Gaussian, life is easier. Same way that we did with measurements, we do with here. We don't have comma here. And here we cost this distance between the position, a start position, for example. Here is a start, like a prior. If you know the start point is mu0, you just need to find the difference between x0 and mu0, and you want to make this minimum. That's it. And that's the cost for that. Easy. For odometry, or actually odometry also called dynamic. For dynamic, you have 2 points, because dynamic factor is between 2 points, two consecutive positions, xk and xk plus 1. But odometry, IMU give you this difference already. So you have these measurements, and from that you find the difference between these two and compare them. Easy. So you can find that as well. The motion model, we had this before in robotics, so we can use the same motion model. If for the odometry we use the same motion model, and we find actually the dynamic model. This is the dynamic model. This is the predicted position, predicted pose, and that's the next pose. So we just need to find the difference. So we can easily find difference between these two and find the residual. That's called residual, and we want to minimize that as well. So that's it. I think there is no time for the code, but next class I'm gonna explain. I just gonna show the output, but I'm gonna show you. I'm gonna explain that next class. This is a GTSAM, how we can define initial values and how define nodes, how define actually factors, and just use one optimization function to just optimize it. We're gonna talk about that next class more. If you have any question, let me know. If not, we can see each other next Friday. We're gonna explain